Hi everyone. My name is Tatas Das, and today I'll be presenting towards my final project for the course EEL6825, and my project's topic is iris recognition for personal authentication and identification, and my advisor for this project was Professor Dapeng Wu. So to begin with, I'd like to highlight a few qualities that make a good biometric system. And we see that a good biometric is characterized by use of a feature that is highly unique so that the chance of any two people having the same characteristic will be minimal. It should also be a feature that is stable over a period of time and is easily captured and used in the system. We see that the properties of the human iris are such that it does qualify to serve as a good biometric since it has unique patterns and it cannot be easily modified. Also, it remains stable over a period of time. So the iris recognition system essentially works on the following processes. To begin with, the eye image is first acquired, then segmentation is applied, where after that normalization is applied, followed by feature encoding, and finally the template of the iris is matched with an existing template in the database, and a decision is based as to whether the match was successful or not successful. So let's go on to the first step, essentially that is a segmentation. And we see that segmentation is done to isolate the actual iris region in a digital eye image. And the iris region can be approximated by two circles, like in the case of HOUGH transform, or the other method for segmentation would be DAUGMAN'S integral differential operator. So these two methods would be explained in detail in the slides which follow. However, through my efforts of implementing these two concepts, I saw that there were a few problems which we could come across while trying to segment the iris in the pupil. And we see that images which are taken under natural light have low contrast, such as this particular image over here, and the HOUGH transform actually fails in this particular case. And also the angle of the image can pose certain problems when you're trying to detect a perfect circle, because it becomes an ellipse in a way. I mean, it's not really a perfect circle when the angle of image is not always straight. So the HOUGH transform is basically a standard computer vision algorithm which is used to determine parameters of simple geometric objects such as lines and circles. And here we use the circular HOUGH transform. A circle with radius r and center a comma b is defined here by these equations. And what happens essentially in the HOUGH transform is that theta is made to sweep from 0 to 360 degrees, and the points x comma y trace the perimeter of the circle. So this way HOUGH transform is used to trace the boundary of the iris and the pupil as shown in this image over here. So a few problems, however, with the HOUGH transform is that the thresholding has to be perfect such that the edges, there aren't too many edges that are detected. And another problem with HOUGH transform is that it's a little computationally intensive and takes a little more time. So for my project, I decided to modify the canny edge detection function, which is done by COSINE, and implement it. So the other method is the DAUGMAN'S method, and this method is highly cited and is one of the oldest methods for segmentation. What this essentially does is it searches in an N3 space for the circumference, center, and radius that have the highest derivative value when compared with that of a neighboring radius. and the equation that it is based on is given here, where I x comma y is the I image, r is the radius, and g sigma of r is actually a Gaussian smoothing function. And DAUGMAN'S method is able to segment better in a way than the HOUGH transform. So then we go on to normalization, where once the iris region is successfully segmented from an eye image, the next stage would be to transform the iris region so that it has a fixed dimension in order to allow successful comparisons. And the way it works is using DAUGMAN'S rubber sheet model, which remaps each point of the iris region to a pair of polar coordinates and enables us to get a uniform representation. So DAUGMAN'S rubber sheet model essentially remaps each point within the iris region to a pair of polar coordinates, which are r and theta, where r is in between an interval of 0, 1, and theta is an angle which is in between an interval of 0 and 2 pi. So the remapping of the iris region from x, y, which are the coordinates of the Cartesian coordinates, to the normalized non-concentric polar representation is modeled by this particular equation here, where I of x, y is the iris region image, x, y are the Cartesian coordinates, r, theta are the polar coordinates, and xp and yp are coordinates of the pupil, whereas xl and yl here are the coordinates of the iris. So after normalization is done, we go on to feature encoding to provide accurate recognition of individuals, essentially. And the way it works is that it works on identifying significant features of the iris, which are encoded and then matched in the next step. So in feature encoding, there is feature enhancement, which is done where blurred images can be sharpened using Sobel filters. Sometimes banding is employed, where bands which are closer to the pupil region are selected. And then feature extraction is employed through methods such as discrete cosine transform or log-Gaber filters. I will be talking about the discrete cosine transform as it has been implemented in my project. So this essentially is a linear transform where the zero crossings of the transform are used, and what it does is it averages the overlapping patches and from the normalized iris images and makes a subset of feature vectors, after which the iris codes are generated as a sequence, and we can employ Hamming distance to match with these subfeatures. So after that, we come to matching, which is the final step in iris recognition, where the test iris image or the person or the subject's iris is compared to the templates which are already there in the database, and output is in terms of positive or negative. Some of the methods of matching would be using weighted Euclidean distances, Hamming distances, or the correlation method. I have implemented the method of Hamming distance, so I will be talking about that a little bit in the next slide. So here, what happens is that the Hamming distance basically compares two templates such that the number of positions by which the corresponding templates are different, and this was chosen essentially because it was easy to implement in a way, and it does bitwise comparisons which are simple. So here the templates are first ANDed with their noise masks that are x of nk and y of nk, and then a bitwise XOR operator is employed, and the two iris templates are compared. On the right here, we can see some of the results of matching template 1 and template 2, and we get a value of Hamming distance of 0.83, which means that they haven't really matched successfully, whereas a Hamming distance value of 0 means that the template is exactly similar. So through my project, I made a couple of observations while working with Hamming distances. One is that even though two iris templates, when they are generated from the same iris code, they seem to have they seem to not have zero Hamming distance in practice for some reason. And what this could mean is that sometimes normalization may not have been done perfectly, or there could be some noise which goes undetected, because of which there are some variations. So that's the reason why sometimes Hamming distance gives you a value like 0.33, which is somewhere in between being matched perfectly and not matching. So that would be all for this presentation, and my demonstration would be in the following video. Thank you.